Good morning, everyone, and welcome back to the second part of the workshop. In the first 2 days, today and tomorrow, we will cover the remaining two topics, manufacturing and energy. We will wrap up on Wednesday this program manager panel, report for moderators and discussion. If you missed the first part of the workshop, the panels, they are available on the workshop website. Now let's start day 4. Saniya and Ed, the floor is yours.
So thank you very much. So Saniya LeBlanc and myself will be moderating this panel or this session. This session is covering heat transfer, manufacturing and thermal transport for manufacturing. We'll have 10-minute presentations by 5 panelists, then the 1-hour poster session and virtual networking in GatherTown, and then we'll break out when we come back to 2 sessions, one on how the advanced manufacturing technologies that we're discussing will impact heat transfer and heat transfer devices. And then the second group will be on how heat transfer and thermal transport affect these advanced manufacturing processes. So we have 5 great panelists. Our first one is Professor Karen Thole. She is the department head of mechanical engineering at Penn State. That will be followed by Young Shin from Purdue University, Kirk Rogers from the Barnes Group, Michael Ohadi from University of Maryland and ARPA-E, and Bill Ulbricht from Cornell and NSF. And so with that, I'll just introduce Karen. She's currently the department head of mechanical engineering at Penn State.
Let's see. All right, good morning, everybody, and Happy New Year. Let's hope for a great 2021. So thank you for inviting me here today. I'm going to talk a little bit about additive manufacturing, and the focus area that I have had over the past few years is to work in this space and using it for convective cooling. Primarily, my main focus has been to use it for the gas turbine, in gas turbine airfoils. So, you know, gas turbine airfoils are incredibly interesting. Lots of different cooling technologies illustrated on the bottom left. Primarily what I'm talking about today is in the high turbine area, which faces some of the highest temperatures that is in the engine. And so there's a lot of different cooling technologies, such as just the airfoil shaping, there's external film cooling, there's ribs, there's pin fins, but you know, in working in this area over many years, you know, it's somewhat frustrating in the terms of what you can actually manufacture and put into a turbine blade for different cooling technologies. So the motivation for using additive manufacturing has really, well, let me say that additive manufacturing has really been embraced by the turbine industry, not always for producing airfoils for actual applications, but using airfoils for development purposes. This table on the right shows a lot of information, but the point is that to develop a new cooling technology and put it into an airfoil and have a single crystal cast turbine airfoil requires about 70 weeks to complete. There are lots of different steps that you have to go through to get the process and so forth. Single crystal cast airfoils are some of the hardest things to manufacture. And to do a ring of blades is about $1 million or more. In contrast, by using additive manufacturing, laser powder bed fusion, which is primarily what I'm going to talk about today, it requires only about 26 weeks, a 2-step process, and only about $400,000. So in a recent workshop, or in a workshop actually in 2017 now, Siemens came out and said that additive reduces the development time for turbine airfoils by about 75%. That's a huge savings in terms of time and cost. So that's really the motivation that I've been working with, or I've had over the past couple of years in working in this field. So you might ask, what happens with when you decide to make a part? And this decision tree, which I know is very small font, this is the decision tree that you have to use in actually 3D printing a part using laser powder bed fusion. So for researchers like us, this is really exciting because there's lots of things that need to be worked on in making a part, lots of different options. And so a few of the ones that we have been focusing on is the laser in particular, the power, the scan speed, this contouring. And then also we've shown that build direction has a huge impact in your component part, in how your parts end up. And as a matter of fact, you know, that we've shown that, and I'll illustrate a little bit about that in the next slide. So this kind of gives you an idea, this gives you an idea of what happens when you 3D print a part using laser powder bed fusion. You can have a slow scanning speed at low power, and you can end up with a surface, something like that, where you have a stable melt pool, you entrain powder, or you could decide that you want to make your part fast using a high scanning speed and high power with an unstable melt pool. As you can imagine, the surface roughness and the surface morphology using these two different strategies ends up being very different. I mentioned a little bit before in terms of the build direction effects, and this is something that my group has worked on significantly. And as you might imagine, when you make a turbine blade, and all the pieces and parts are going to be built at different angles. This just does a simple illustration of taking a part and going from 0 to 90 degrees with different build directions and showing how the ultimate microchannel results. You can see that with a 0 degree or a horizontal build, the roof caves in, whereas the 90 degree, you get a shape something looking like this. Still not a circle, you know, perfect circle, but it certainly has, you know, a different shape. The other thing I'll illustrate here on this histogram is that you can get a wide range of different shapes throughout the channel. This is a CT scan of each of these channels, and you can see the histogram in terms of what the diameter really results in. While we were aiming for a diameter of about 1 millimeter, you can get a wide range of diameters. So the controls of making especially small parts is pretty challenging. So I know many of us have worked in heat transfer for many years. So this is a plot that shows the heat transfer augmentation versus the friction factor augmentation. And I've used some of the data from the literature here with highly engineered surfaces. And I know I saw Leslie Wright on the line. And so some of this is her work at Texas A&M. And you can see that, you know, for these shapes, you get a particular performance. So you get so much pressure drop as so much heat transfer augmentation. All of these open squares, in fact, are just microchannels made using additive manufacturing, not highly engineered, but just manufactured. You can see what's pretty exciting is that while we haven't done anything to augment the heat transfer, you get about the same performance as what we would call a very highly engineered surface. So that's pretty exciting for people who work in heat transfer. So another then kind of illustration to show the effects of manufacturing, you can see these two graphs here on the left. Again, this is a friction factor augmentation versus Reynolds number, and this is a Nusselt number augmentation versus Reynolds number. Just by setting different manufacturing process parameters, you can end up with very different surfaces, surface roughness. And in fact, you can get pretty dramatically different heat transfer augmentations and pressure drop augmentations. And this is all controlled through the various process parameters that happen with additive manufacturing. This is some of our latest work. The other side of this is to start using optimization methods. And you know, now we can build lots of different shapes. So this was a really simple study where we took all kinds of different shapes and we built them at different build angles. And you can see that some of the shapes ended up pretty well and some of the shapes didn't end up so well. But you know, we learned a lot from this study. Again, build angle is very important. On the right, is some joint work that we've been doing with the University of Texas, who has been doing some optimization of film cooling holes, the small holes that are placed in film in turbine blades, and looking at some unique shapes. But we wanted to understand, can we build those? And this is a contour of a built AM optimized film cooling hole shape, where you can see the colors actually represent the difference between the design intent and the actual build that happened. So you can see that this is an illustration, but you can see that we were able to build some pretty unique shapes using additive manufacturing. So finally, I'll end maybe with two more slides. One is, just talking about the research challenges. Certainly the surface roughness is a challenge, but you can also use it to your advantage, especially if you're trying to augment heat transfer. But it doesn't augment, the pressure drop and the heat transfer do not augment at the same amount. There is some, I think, real challenges in printing accurate small features. And there certainly could be some work done in that area. I think that there's a lot of interesting things in terms of using AI and machine learning to enhance builds. So as you're building the process and as you're building the component, making direct measurements and how that feeds into your build. I think that is a wealth of really interesting areas. We desperately need AM materials for high temperatures, and that's really what is stopping the use of additive in many applications. So there's a lot of work that needs to be done in that. And then there is another really great opportunity in, I didn't talk about it today, but to integrate sensors in instrument, or integrate sensors and instrumentation in the additive part directly, which allows us to make some measurements that we have not been able to make before, especially in complex turbines. The implementation challenges are, there is some component repeatability for production. That is really quite challenging. To get the same part every time and get it, especially on the production side. And then I think, I know a lot of academics are on the phone, are on the line here, just to teach our students in thinking differently about design of parts. We have round microchannels because we have round drill bits. But there's a lot of interesting work that needs to be done on the education side to get our students prepared to make a difference in the workforce. So I think I used my 10 minutes, so I will stop here.
Thank you very much. That was great. Can Professor Shin present, or can you share your slides? Okay, while we wait for,
Hello, can you hear me?
Yes, please go ahead.
Okay, great. Okay, so I was worried. And okay, so let me here swap the screen. So is it okay? Can you see the screen? Okay, so my name is Young Shin from Purdue University, and I'll be happy to share some of the things we have done, and also present some of the issues that we have to address in the future. And I have been working on various areas of laser-based, manufacturing, material processing, and so I highlight some of the areas that we have been working on. And in this presentation, I'll be mostly talking about laser additive manufacturing. And I already say that lasers can add subtract and transform materials. So it's a really versatile form of energy here. And in metal additive manufacturing, we can include largely the powder bed fusion and direct energy deposition. And you can see some of the parts that can be fabricated by these by the additive manufacturing processes. You can build very complex parts. Also, you can build the functional parts. The one of the grand challenges in the metal additive manufacturing in particular is that to understand the process of microstructure property relationship. So we have many parameters that affects additive manufacturing processes, such as operating parameters and feedstock materials and scanning pattern, all these things, which will affect the thermal history here. And this thermal history is very important because it affects basically microstructure during the solidification. So once you have the microstructure, then this will basically dictate the mechanical properties. So in order to be able to control the mechanical properties, we really have to start from upstream and be able to predict all these things, establish the relationship. That way we can avoid large lead time and many trials and errors. Otherwise, additive manufacturing is going to be a very expensive process there. So over the years, we have been working on the modeling and linking all these things. So this is our additive manufacturing process modeling roadmap. So we start from this thermal model here and try to predict the thermal history and particularly the free surface geometry during solidification. And then we try to also predict the resultant microstructure based on the thermal field, and then finally try to predict the mechanical properties such as residual stress, thermal distortion, and mechanical properties. So this is what we have been working over the years. And this is very vertically integrated. If you look at this one, and you start from the material and you have a laser power input coming in, then you have a melting, evaporation taking place, and you will have basically cooling, solidification. Finally, you'll have a microstructure that affects the stress strain and the geometry and mechanical properties. So not only this is complex problem, and if you try to predict these things, we have to deal with the multi-physics, multi-scale problem, because some of things you can actually model at the macro scale level, but some of things you have to go down to really a micro scale level or even the nanoscale level to be able to predict these things. So I would consider this one as a multi-scale, multi-physics modeling problem. So just not to bore you with something, but if you really try to predict something here, then you have to have some sort of a free surface tracking mechanism, and also you have to have a mass, momentum, energy equations, and you can actually combine all of those things and actually predict this one. So this is one of the examples of the modeling effort that we have made over the years. So basically, you start from here, powder flow in direct energy deposition. You try to predict how the powders flow and then how the powder temperature is elevated due to laser heating. Then basically, and the next stage, what you do is you predict the molten pool and the predict the temperature field, and then you actually predict the free surface here. So in this case, three things are important. One is that predicting the free surface here, shown by yellow line, and the other one is a fusion zone, shown by the red one, and the third one is here heat effective zone, and shown by the green line. All those things need to be predicted accurately to be able to predict the microstructure and the thermal history accurately. Another example that I want to show here is the powder bed fusion. The only difference in the powder bed fusion is that how the powder is placed instead of blown into the molten pool. And so you have to basically model the powder placement, and we use a discrete element method to do modeling of this one. Then the remaining portion will be pretty similar to direct energy deposition. Only difference here is that in the direct energy powder bed fusion, if your power energy density is above certain threshold, you may have a keyhole. This is very undesirable. and leading to formation of a porosity and other things. So you have to control this one, avoid the formation of the keyhole. So it's important to include this keyhole formation and during the powder bed fusion process. So if you show some example, if I show some examples, so these are some of the prediction results. And you can see that how that the molten pool is formed, and you can see the side view of the free surface. And this is actually front view of the free surface. And once you can predict these things accurately, you can use this one as input to your certification model. And when you have a keyhole, the problem becomes a little more complicated, because what happens is you have basically a large amount of metallic vapor formed, and then you also have here multiple reflection through the keyhole, and you have a plume generate that started interacting with the incoming laser. All these things need to be considered in the model. So once you get that the thermal field, you can use that as an input to predict the resultant microstructure. So this example shows the large-scale prediction of a microstructure using cellular automata technique, and you can see how we were able to predict this one and that one. Okay, so next one here I'm going to show you is that you want to predict the details of the microstructure. Cellular automata technique is not sufficient because it's suitable for the larger domain problems, but it does not capture the details. So you can also use something like a phase field modeling technique to capture details. So I'm going to show one example and also talk about the problems associated with this one. So this is actually three-dimensional prediction of a detailed microstructure for aluminum 6061. And the domain we use is very small. So this is a small domain we use for prediction, 7 micron, 14 micron by 28 micron. And you can actually predict the microstructure evolution here, and pretty accurately. The problem is extensive amount of computational time. It took 60 days on 20 processors. So although this is a very sound approach, the problem is the computational requirement is too extensive. So you cannot really use this one for part level prediction and of a microstructure. So once you get the prediction, and using this type of a 3D phase field model, you can capture the details of a microstructure. That's very good. But like I said, it'll be very computationally extensive. So you can only do the prediction at the very local level. Okay, so I know we have a limited amount of time, so I will have to skip some of the slides I have here and then go to the directly to the problem statement here. So what are the critical challenges in AM modeling? We need to have more accurate, reliable, integrated multi-physics models. We don't have something like that one. So people are still relying on trial and error and experimental approaches. So lead time is very extensive. And if you use some of the commercial systems, and these OEM people do not even allow you to change the parameters because they are concerned about producing defective parts. So we should be able to predict the thermal transport phenomena along with the result of the microstructure phase, defects, form accuracy, finish, residual stress, other mechanical, chemical, thermal properties. Right now, a lot of people are working on modeling, but these models are very fragmented and they are not integrated. That's one of the problems. The second problem we are facing is that extensive amount of computational requirement. And currently, it's not possible to use high fidelity model to predict the set of thermal field or microstructure at the part level. So the question is that, do we have to use a high fidelity model, or can we use a low fidelity model, okay, to predict the part level thermal field? The problem with the low fidelity models can only provide trends, not the accurate enough information. That is a problem. Also, we need some experimental, improved experimental technique for in situ measurements of temperature, flow of particles, fluid, gas, and plasma dynamics. This is to gain further insight into the underlying physics, also to validate the predictive models, also to guide the future design of process conditions. So this is very much a needed area. Another area that we need to address is the properties of the material. And we need to have a more accurate sort of a measurement or prediction of optical, thermal, electrical, magnetic properties of material. And without those things, you cannot really have a good prediction of the models. And the other thing is that we need to have a more accurate validation and certification standard, and that people can use to validate their models, also to certify their additive manufacturing processes. So this is my last slide. I'd like to say that we have a future research need in developing predictive models that can guide experiments, not the other way. A lot of times we actually develop the model and experimentally validate one, but true purpose of the modeling is to guide experiments, so we don't have to do so many experiments. So we need to have that one in the future. And so second thing is that we may have to also incorporate data-driven approaches, combining high fidelity, low fidelity modeling result with the experimental data. This might be the way to go to improve the computational efficiency that we're currently facing as a challenge. Also, we need to have a better experimental techniques. Also, we need to have a better optical, thermal, magnetic surface tension types of property calculations or measurements. Okay, so that's my last slide. Thank you.
Thank you very much. I actually forgot to introduce Professor Shin. He is the Roche Distinguished Professor of Advanced Manufacturing at Purdue University, where he's a professor in the Mechanical Engineering Department. Thank you again. Our next speaker is Dr. Kirk Rogers from the Barnes Global Advisors. Kirk, do you want to try to share your screen one more time? And if not, I can, yep, you got it.
Yep, I did decide to restart my computer and close the 100 other things that I had open.
So Dr. Rogers is at the Barnes Global Advisors, where he's a technical excellence leader. He had a 20-year career at GE, working in medical device manufacturing, and really built up the AM business there. So go ahead, Kirk. Thank you.
All right. Thanks, Ed. So realistically, I'm going to take a slightly different tact than the last two presenters, although I think they hit the needs very, very appropriately. You know, a few years ago, my team at GE was testing commercially available, low fidelity codes for additive, and we decided that it was actually faster to build, measure, and then redesign than it was to simulate, with low fidelity models 5 years ago. That's not true any longer with some of the mechanistic models, but it is still true with microstructural level modeling. Really, Barnes Global Advisors is a small consulting company. We work with universities, with big companies, with little companies, with startups, and with investors. So what I thought I'd do today is give a little perspective of the industry side of things. And we hear additive manufacturing, and many of us default to laser powder bed fusion, but additive manufacturing is much more than laser powder bed fusion. And so a few examples here of a very small. So Nanoscribe is a company that made the Eiffel Tower on the left, and they use single photons of light to polymerize materials, right? So that is literally a scale model of the Eiffel Tower that's a millimeter tall, right? Two things in the center like dresses and topology optimize, shapes for either design purposes, to, things on the right where construction materials are starting to be 3D printed for, low-cost housing, both in the US, Europe, and even more significantly in China these days, right? And so the reason why AM can do such a wide variety of things is that there's really 7 known categories per ASTM F42 committee. right? And here they're pictorially shown, and the ones that are really useful with metals and may be interesting to this group, we put with a star. So material extrusion, binder jetting, which I don't think we've talked about at all. Powder bed fusion is very common for its ability to make high fidelity features, right? Directed energy deposition, which our Purdue professor was just talking about to some degree. In this case, it's most likely going to be powder fed because the ability to make fine features, right? But then tools like sheet lamination, right, are also very useful at making relatively complex structures, but it's not yet commercialized to a broad extent. And so because of the variety of different tools available, and we can do a variety of different things by additive manufacturing. If we look at the industrial side, has really been pushing the knowledge, I'll say, versus the academic understanding of the fundamentals of the various processes. And so, that's because of the practical usefulness, which I think our first presenter, talked about turbine blade applications, where the ability of additive to help development go faster was really the driver for adoption, and that is one of the key drivers for adoption. So here we have a graph of a couple different materials, right? And sales are moving dramatically faster in industry on materials, and pricing is reducing, right? So here's titanium, stainless steel, and nickel pricing for powders for essentially laser powder bed fusion or directed energy deposition type AM applications. And so the reduction of price means that more industries are adopting additive, and that's changing the shape of what materials. So powdered metals were only available 10 years ago in aluminum, nickel-based superalloys, and some steels and some corrosion-resistant materials. That is changing quickly. Titanium has a great interest, Ti-64 primarily, from the aviation and other high performance industries. And so metal powder went from not being a thing in titanium to being a significant portion of the AM metals market in the last 5 years. If we look forward to more like 2025, things like copper, stainless steels, carbon steels are becoming a much bigger part of what's happening in industry. And we're moving more from those custom materials, right, to standard engineered materials that are used by just about every manufacturing firm on the planet. And so that's interesting, from the perspective of broadly available materials, which is not the case today, but will be in the next few years. And the other sort of grand trend that we see is things like glass and optical fibers being printed, right? And so, highly transparent optical materials that can be 3D printed into innovative arrangements is a really cool thing that's happened in technical ceramic side. Right, I already mentioned the concrete printing, and this is something that's just starting to come online. It's probably not important to this audience, but it's something that's important to share, that we understand the scale of 3D printing is not lab scale anymore. It's physical, real scale in many materials, not just concrete, but in rocket engines and that sort of thing. The other kind of interesting industry side thing is that there has been a ton of investment and M&A, a merger and acquisition activity in the 3D printing area to the tune of about $25 billion in the past 5 years, which is a significant sum for a tenth of a hundredth of a percent of the total manufacturing. Right. So we already saw a couple of use cases, so I won't spend any time here. Turbine blade being an great example. Mesh structures, implants with osteo integration features are pretty commonplace today. What's really driving in application spaces is the integrated thrust chamber kind of things for rocket motors that we're starting to really see as the the race for going to Mars is speeding up, and the desire for space tourism is driving significant investments by companies like SpaceX, right? The other thing I would like to point out here on this page is the heat exchanger in the bottom left, right? So that's a more or less conventionally designed heat exchanger, right? It's about 1/5 of a conventional, brazed wavy plate, straight plate heat exchanger, and it weighs 85% less mass for the same performance. And so we see this over many different applications that I worked on at a couple previous gigs. The average heat exchanger moved from conventional to additive was 30% less expensive, 30% more efficient, and 30% smaller, in the additive side versus the conventional methods of manufacturing. Added to that it's many fewer steps of assembly and manufacturing to get to an additive heat exchanger. It's becoming an area that is widely commercialized, and there's several specialist companies that all they do is heat exchangers using laser powder bed fusion. So here's an example, just a quick example of what's happening in industry today. So we had a quickie project earlier this summer where we got approached by a company that's trying to make the Keurig of ice cream makers, and they had designed this part that was unmanufacturable by conventional means. And so they said, hey, can you guys print it? And we said, sure, we can print it, but that's not the best way. Why don't you have us redesign it? And so we used 3 different topology optimization tools to try and come up with a generative design. Sorry, I'm using the wrong term there. We use several different tools. Here's the best case design, right? And that best case design looks completely different, has exactly the same function, right? But it's 87% less mass. It's 36% faster to print than the non-printable design, right, or the non-manufacturable design. It's consolidated a couple of parts without really trying, and eliminated an assembly step with 3 fasteners. So from a commercial advantage, that's huge. The other thing that we're really starting to see with the generative tools is heat conduction generative design being commercialized. So Paramatters is a company that we often work with. Here's their heat conduction generative design example, right? You see the design on the left and the thermal profile on the right. It's maybe not perfectly optimized, but it looks very different than, a conventional heat exchanger. And what's coming in 2021, now that we're in 2021, is coupled thermal mechanical design will be available in their tool, which then brings a ton of advantages where, for a few dollars and a little bit of cloud computing time, you come up with a very cost-effective, very interesting design. And another kind of oddity that we've been working on that's interesting from a thermal perspective as well as filtration perspective is building 3D printed structures with very specific porosity. So you could use that porosity to control thermal performance. In this case, we really were optimizing for best filtration performance early on this year, early on in the pandemic. This was an effort to make a permanent filter. It's been the design and activity has been proposed as a SoftWorks project to the DoD and is awaiting funding. Similarly, right, high temperature heat exchangers are a huge academic exercise. And so right now we're working with Carnegie Mellon and UC Davis on high performance supercritical recuperator for CO2. Right? And so this is an 800 degree C application, heat exchanger, very novel kind of pin and plate designs, designed from the beginning to be 3D printable. And we're working towards from a 5 kilowatt demonstrator in nickel-based superalloys to next generation materials and next generation printable designs to get really a very compact 50 kilowatt demonstrator here over the next couple of years. So, from my perspective on the commercial side, AM is bright, future is bright with, commercial tools being available for design and optimization, right? Copper and some other high thermal conductivity materials are available and being integrated into products as we speak. The opportunities, as I think was mentioned before, is really, high temperature AM materials are not well studied for their thermal performance, and there's opportunities for new materials that actually we've proposed a couple of NASA projects over the past years that haven't been funded, unfortunately, and the opportunity that Karen definitely mentioned in education, right? Simple things like holes need not be round and design for additive are huge barriers to the next generation of performance. All right, thank you.
Great. Thank you, Kirk. And that last slide is a good lead in to our next speaker. Our next panelist is Dr. Michael Ohadi. He's currently the program director for the US DOE ARPA-E, Advanced Research Projects Agency for Energy, where he focuses on heat and mass transfer enhancement and process intensification, utilizing innovative designs, materials, and manufacturing techniques. He's currently on leave from his role as a professor of mechanical engineering and the co-founder of the Center for Environmental Energy Engineering at the University of Maryland in College Park, where there his research involves active and passive process intensification of single-phase and multi-phase fluid thermal systems using innovative design, materials, and manufacturing. So Dr. Ohadi, I'm going to hand it over to you. You should be able to share your screen.
Thank you, Sonia, for your introduction, and thank you for the organizers to give the opportunity to be here and talk. Let me see if I can share my screen here. Is it okay?
Yes, we can see.
Can you see my? All right, thank you. So I thought to case example, 3 case examples that really design for manufacturability and materials were the key component, without which we could not achieve the metrics that we had signed for the program. Each of these programs we spent about a year studying, simulating, reaching out to industry, academia, and practitioners to get their feedback before we put the metrics together. So I know time is very limited, and I'll be going quick through some slides that I'll put together. Again, something that is unique to ARPA-E is we work in teams with different backgrounds. In this case, Dr. Zach Fang, material scientist, David Tu, aerospace, and then we have technology to market and tech CEDAs and program managers handling the HITEMMP program. So why high temperature? I think it was in early 2000 that one of the colleagues and I wrote an article arguing we need higher temperature. The reason is very clear. If you look at Carnot point of view, and if you're trying to get 80% of Carnot or whatnot, the higher the temperature of the heat source, the better your efficiency. In general, the aerospace industry will tell you for every 45 degrees C temperature increase, or about 100 degrees Fahrenheit, you get 1% efficiency improvement in the cycle. So that is huge, because 1% efficiency improvement would mean tremendous savings in energy consumption, in CO2 footprint, in water consumption for power generation plants, and so forth. Any effort to increase the temperature at the source would be naturally directly translating to good results. I'd like to remind you with the fact that typical fuel that we burn, you are burning as much as 2,000 to 3,000 degrees C, and then you rush to cool it down to the material level, be it stainless steel or be it some other commonly used materials, which are much lower than that temperature. So the result would be substantial waste heat to the extent that you have seen all different charts, that far greater than 50%. In fact, 2/3 of the energy that we generate goes to waste heat, and only 1/3 is usefully utilized. So energy generation at higher temperatures, yes, can reduce your losses. So it's not really an academic dream. Industry has been wanting this for years. The chart to the left shows you the trend. The temperatures are increasing. They would want to be operating at higher temperatures, but in fact, this chart points out that we are behind the dreams of much higher temperatures. And so we looked at these problems. Of course, there is a lot of work that has been done in turbine blade, and Professor Karen Thole did mention that as such, and a lot of progress has been made there. But let me see if I have a slide here. Right, we did a sensitivity analysis. It is really the heat exchangers immediately after turbine inlet temperature that are driving the limitations. So we do not have heat exchangers that have good power density. Neither do we have heat exchangers that can survive the environments of high temperature and high pressure. So I mentioned high temperature and the direct benefit of it. What about high pressure? If you're able to utilize high pressure on the hot and cold side of the heat exchanger, there are tremendous benefits that come with that. For example, we could use, as it shows to the left side, we can use supercritical fluids such as a CO2. As you can notice here, the pressure ratio is only about 3, whereas if you go to a steam cycle, that pressure ratio is much higher. The result is you have so many stages in a typical gas, in typical steam-driven turbine versus supercritical. So potential for compaction and size reduction is huge. That's an area of interest to ARPA-E and to the country, because for every pound of mass that you reduce, there is tremendous savings at the source and tremendous savings in transportation and tremendous savings at the site when we utilize processes. So for process intensification, we need higher pressures and supercritical fluids to achieve that. Many applications can immediately benefit from. Aerospace always, as usual, looks for lighter weight, smaller devices, both in the civil section and as well as in defense applications. Nuclear, solar, petrochemicals, marine transportation, and just about all the sectors can benefit if you're able to introduce lighter and cost-effective heat exchangers. So the problem with, I think it was mentioned by Professor Karen Thole, as well as our most recent speaker, that we do need high temperature heat exchangers that can also survive the extreme conditions. As you can see from this chart, pretty standard chart that many of you may have seen, the moment you go past 550, 600, or 700, you see that the strength of this material substantially drops. And that includes for some of the superalloys that are listed here. Now, at the same time, these superalloys are far more expensive than your commonly used materials. And they're a lot more difficult to machine. So we really do have a what we call ARPA-E hard challenge in terms of utilizing a heat exchanger that achieves the life cycle durability as well as performance. So the metrics that we set for these heat exchangers were realistic. Goals are achievable. They're not impossible goals, but they're quite challenging. For example, the previous speaker mentioned that one of the projects they're working on, they're developing heat exchangers. To this date, we do not have any of the teams. Out of 13 teams, in fact, one team already stopped because progress was not sufficient. We do not have any of the 12 other teams to have achieved the metrics. Granted, it's only a year or so into the project, so I'm confident we'll have at least 2 to 3 teams that will achieve these goals. But you are starting with power density today of about 0.5 to 1 kilowatts per kilogram. So we are trying to make this heat exchanger much lighter. So no surprise that yes, as of today, we are not really recuperating waste heat in a typical aircraft, because by the time you calculate the gains that you get as a result of recovering efficiency and how much extra weight you have to lift, people do not find that cost effective and they forget about it. One of the challenging aspects of our program is cost. It was mentioned by both of the previous speakers, but just about all previous speakers, that one thing in AM that is challenging and we need to overcome is the cost and the speed of manufacture. And I think in this case, our costs are pretty challenging. But again, I'm confident that we will have 2 to 3 teams achieving these metrics. And we do not have a single team that is not multidisciplinary as such. So yes, just a reminder that innovative designs, materials, and manufacturing was certainly needed for this program, or else we could not get close to achieving the metrics. So as we were selecting the projects, we were careful not to choose all the projects in one sector. As you can see, a good number of our projects are in AM. However, we do have 5 other manufacturing techniques that are making very good progress, and people have proposed and are making progress on. In terms of the materials that we're looking at, again, you see a diverse list of materials, high temperature materials, including 3 ceramic solutions that have their own manufacturing aspects and manufacturing challenges. But if they do come along, they are very light, can take extreme temperatures, and as such would be very low cost as well when and if they do happen. So as I look at our projects, no shortage of good designs, no shortage of innovative designs. I think we've been pretty pleased to see the innovation in that front. No shortage of materials for range of temperatures that we're looking for. 800 C for metals, 800 C and greater for metals, 1100 C or greater for ceramics. So no problem there, but manufacturing remains the problem. And predominantly the fact that a combination of thermal fatigue and creep comes into this condition, because it's not just thermal stresses that are at play, but also creep. So the macrostructure that takes both into account and the topology that takes both into account is quite important to make this succeed. I'm running out of time, so I will be very quick here. A second program that manufacturing was definitely a need, or else the metrics could not be achieved, is an aviation program that we have put together. Ascent and some 10 teams are recipients. And in Ascent, the need once again was for distributed power, which means many electrical motors that are light. So compared to today, where a gas turbine is producing 34% efficiency, our system would have 60% efficiency. But the typical electric motor currently is at 5 kilowatts per kilogram, best in class Siemens motor, whereas the minimum that would achieve our metric would be 20 kilowatts per kilogram for the electric motor and 30 kilowatts per kilogram for power electronics. A typical motor is nothing but putting more current density in and as avoiding saturation. So the shape of the winding is very important. And to our surprise, to our pleasant surprise, not to me as a thermal management person, but to the ARPA-E leadership being convinced that thermal management was the bottleneck, nothing else. Thermal management was the bottleneck to developing high density, high power density electric motors. So we're looking into, we did some simulations you can see here, where state of the art is additive manufacturing of windings and advancing materials insertions and cooling technologies and so forth. And so the simulations projected for us the role of each of these, and on that basis we set our metrics so that we are not really envisioning impossibles as such. So we look forward to reporting on Ascent results as the results become available. And lastly, and my last slides, I know Saniya is anxious for me to finish here. It's a program that we recently put together. Submissions have taken place, but we have not selected projects yet. Is topology optimization of thermal management systems. Again, this is extreme environment conditions, very high temperature, very high pressures, and the application of inverse design, additive manufacturing, and topology optimization would be at play. Very important to distinguish between shape optimization and topology optimization. Shape optimization will not do it here. Topology optimization is the one that will do. So in summary, I've been really excited working 4 years at ARPA-E, having finished 4 years at ARPA-E, now into 5th year. The role that thermal management has been playing. And my colleague Peter de Bock will be on Wednesday also a panelist, the incoming program director, that would be discussing all the opportunities, but plenty of more opportunities, plenty of more programs that you could help the agency and other government agencies define innovative solutions that you may bring to the table. Thank you so much.